Thank you for taking the time to join us on this webinar to discuss how REXA can improve the operational performance of your coal-fired power plant. My name is Rich Rochford. I handle the power industry for REXA, and I'm pleased to have the opportunity to introduce our technology to you. Buddy LeMasters will share some of his successes with us on plant upgrades and how they have affected Longview Power. Buddy, before we begin, can you tell us a little bit about yourself and your responsibilities?
Sure, Rich. Thanks for the introduction. My name is Buddy LeMasters. I have worked on and around power plants for 23 years. My experience covers everything from construction, startup and commissioning, plant operation and maintenance, to engineering and reliability. I have been with Longview Power for 10 years now. For the first 6 years, I was the IC&E supervisor, and now I work in the engineering and performance department, heading up various projects for plant efficiency and reliability improvements.
Thank you very much, Buddy. With that, I'm confident you'll find the webinar to be informative, gain valuable insight on opportunities in coal-fired power, and have a better understanding of REXA technology. So let's get started. For the webinar agenda, the topics we will be going over include an overview of coal-fired plant industry trends and drivers. Though coal-fired power is trending down in many areas of the world, it remains an important and critical source of baseline power for grids worldwide. Typical plant designs. We'll review the 3 basic coal plant designs and the differences between them. Actuator types used. To better understand the REXA technology, we need to look at other types of actuation to distinguish them from what we do. A history of REXA. It was from the need to combine the benefits from each type of actuation technology that REXA originates and eventually took shape. A review of electrolytic technology. We'll look at the inner workings of the REXA actuator and what makes us the most unique technology on the market. The Longview Power Plant, one of the newest coal-fired power plants in the USA, will review some baseline information and statistics of Longview Power. Operational challenges in cooling tower performance. Longview is experiencing problems with a cooling water makeup valve and controlling temperature. We'll talk with Buddy and learn how much this issue cascaded back to the plant and impacted operations. System improvements and benefits. Who would have thought that gaining control of water temperature from the cooling towers back to the condenser could improve plant efficiency and ultimately heat rate? Buddy will share with us how all this came together and the many system improvements that were recognized. And finally, we'll wrap up the webinar with some key takeaways and answer a few questions. I wanted to first touch on the status of coal-fired power around the world with focus on some of the larger players. This beginning slide shows information on trends that are quite eye-opening. The International Energy Agency predicts that coal will surpass oil as the world's most popular fuel by 2022. There has been an increase in coal use due to extreme growth in emerging markets like China and India. Cheap fuel for electricity production is important, so quickly growing infrastructures can be supported. Notice in the center of the chart that no other country is even close to the amount of coal that is used by China. China is by far the largest coal consumer and accounts for more than half of the global consumption. The International Energy Agency predicts that China will have an increased demand for coal of between 2% and 3.7% per year for the foreseeable future. Though solar and wind power is being added to the mix, coal-fired power plant projects currently under construction total approximately 190 gigawatts. Next is India. Though it is unclear how many of the 370 coal-fired plants in the planning stages will be built, 70% of the country's power comes from inexpensive coal. India ranks number 2 on the list for installed coal plant capacity. A number of the plants being built are the more efficient and lower emissions supercritical design. South Korea. Despite efforts to boost renewables and natural gas, Asia's fourth largest economy currently generates 45% of its electricity from coal. 7 new coal-fired plants are planned to be built by 2022. Southeast Asia. One of the fastest developing regions in the world, electricity demand will grow by 83% in the next 16 years. There are 120 coal-fired plants under construction and more than 240 planned. The Middle East. The United Arab Emirates will build 11.2 gigawatts of coal-fired plants by 2050, increasing electricity by coal to 12%. Egypt, Iran, and Turkey are also planning to build additional cleaner burning coal plants as well. Closer to home in the US, many of the coal plants shut down in the last 10 years were smaller and older. It is most probable that coal will be generating as much as 22% of electricity in 2050. Europe. Currently, coal-fired power makes up 26% of the European Union generation. While there is a push to increase renewable energy, efforts are slow, but underway to upgrade existing plants to be emissions compliant. Coal will be needed for decades to come to provide stable energy to the grid. And finally, South Africa. Over 90% of the power in South Africa comes from coal. It's a continent that is still trying to catch up to the developed world. It's believed that renewable energy is far off in the future due to the tropical wet climate. In South Africa is also a major exporter of coal and exporter of electricity to neighboring countries. In summary, coal-fired plants will remain an important source of power worldwide for the long term. Many countries are coal dependent, such as South Africa, China, India, Indonesia, Poland, and even Australia. The power is reliable and the cost is reasonable. Overall, there are 1,600 coal plants in 62 countries that are either under construction or planned. Okay, let's switch gears. For the benefit of those attending this webinar who may be unclear of the differences, let's look at a quick overview of the 3 basic plant designs. First, a subcritical plant or boiler operates below the critical pressure of water at 3206 psia in 705 degrees Fahrenheit. The subcritical boiler design goes back to the early 1900s and includes a steam drum where the steam loop begins and ends. With a natural circulation through the tubes due to a density change from water to steam, water is boiled only partially, protecting the tubes. Steam is then drawn off the steam drum, sent to superheaters, and onto the turbine. These are smaller plants and usually operate in the 32 to 35% efficiency range. Supercritical boiler technology came later in the 1950s. A supercritical boiler operates above the critical pressure of water where there is no difference in the density of water and steam. There is no steam drum. Water is immediately turned to steam in the tubes. Circulation is once through the tubes, accomplished by using a pump. Better grades of materials are needed to accommodate these higher pressures and temperatures. The preference in supercritical boilers is that they are more efficient than their subcritical counterparts at greater than 42% and have lower emissions. These plants are typically larger and above 500 megawatts. Ultra supercritical boilers take these higher pressures and temperatures to a new level at more than 4,200 psi and 1140 degrees Fahrenheit. Their operation is practically identical to the supercritical design, with a bump in efficiency up to 55% and further reduce CO2, NOx, and SO2 emissions. Now that we've reviewed the coal-fired power market and basic plant designs, let's look at the actuator technologies found in these plants. There are three types of actuator technologies: pneumatic, electromechanical, and hydraulic. Each uses a different method to develop forces and create motion, all with advantages and disadvantages. First, pneumatic actuators normally installed in balance of plant equipment are the most common in modulating applications. Their advantages include low purchase price, and some models are capable of fast stroking speeds. However, there are limitations of using pneumatics. With air as the compressible medium generating force, it is very susceptible to changes in air quality, the major culprit being moisture. And the air needs to build up in order to create motion. The results are losses in resolution, overshoot or undershoot, and increased dead time. Add a smart positioner into the mix and dead time does improve, but resolution takes a big hit. Next is electromechanical actuation, most commonly found in on-off type service, which provides tighter control and better frequency response than a pneumatic actuator. However, electromechanical actuators can have limited duty cycle, usually around 25 to 30%, limited force or torque output, and very few fail-safe options available. In addition, the mechanisms involved for rotary to linear conversion are troublesome, especially in high thrust applications. Using hydraulics is the most common method to operate turbine governor control valves and turbine bypass valves. These systems provide high frequency response, fast speeds with low dead time, high resolution, and fail-safe capabilities, making it ideal for this type of service. These benefits, though, come at a cost. Oil volume is typically very high and requires routine oil maintenance. Most hydraulic systems are open-looped and have similar types of components that include a reservoir to draw oil from and discharge to, and filters that maintain the hydraulic fluid's optimal properties. Many issues with an HPU system can often originate from the breakdown of the hydraulic fluid. An area particularly susceptible to contamination occurs in the sump or reservoir. It's here the hydraulic fluid is exposed to the atmosphere that includes moisture and particulates. Components like servo valves are very sensitive to changes in hydraulic fluid quality. REXA combines the benefits and capabilities of each of the actuator technologies into one. The simplicity of pneumatics, compact installation of electromechanical, and the fast stroking, high resolution, high duty cycle of hydraulics. How REXA came to be was from identifying control issues in a process loop and looking for methods to fix those problems. Valves were often, and still are, blamed for poor control in a process. What if the valves were not the only reason for having control issues? Robert Glamoux from Mason-Nealon recognized that other variables were at play and had a passion to come up with a solution. He emphasized it was the final control element, the portion that controls the valves and gates, that was the area needing improvement. So, it was in the early 1980s that he set out to develop a technology that had to be accurate, stable, simple, and compact. The result was the patented flow match valve technology, also considered the heart of the REXA. From that point, the linear actuator was completed with rotary and drive units to follow. And for those wondering, the name REXA actually stands for Roberts Expert Actuator. Okay, let's talk about some benefits of the trademark name electrolytic actuator. To start with, it's a very unique design unlike anything on the market today. The true closed-loop hydraulic system is pressure sealed with oil volumes approximately 95% less than those found in a standard HPU. There are no filters or oil changes required, making it very maintenance friendly. All models are 100% duty cycle through the use of brushless stepper or servo motors. These units are high precision and repeatable to 0.05% of span. Our modular design allows for very high thrust and torque output with high-speed fail-safe options. Operating temperature range is minus 40F to 250F without performance degradation. And having passed rigorous testing for the US Navy, Rexa actuators are unmatched when it comes to being rugged and reliable. The electrolytic technology consists of two primary components, the mechanical subassembly and the electrical subassembly. The mechanical portion is attached to the driven device, which in this case would be a butterfly valve. The electrical assembly is basically the positioner for the actuator. This is where the main power supply and control signal are routed and the origination of 4 to 20 milliamp position feedback for connection to the DCS or other control system. We separate the electric and mechanical assemblies for ease of access and operation. There are many severe applications, for example, in mining and desert environments, where onboard electronics simply would not survive. The control box can be mounted in a convenient location to the valve or up to 700 feet away. Okay, let's take a closer look at the Rexa hydraulic circuit. This is the real area of differentiation with our technology in comparison to HPU-based electrohydraulic systems. The centerpiece of the electrolytic circuit is our bidirectional gear pump, which is coupled to the Rexa brushless motor. The gear pump works in conjunction with the flow match valve, which is designated as FMV1 and FMV2 on the schematic. It is important to note, from a size perspective, the flow match valve and the gear pump can each be held in the palm of your hand. During operation, when the actuator is at the desired position, spring-loaded ball check valves are locked in place to prevent the flow of oil through the flow match valve. But when there's a signal change, the motor activates, turning the bidirectional gear pump, which instantaneously builds pressure, allowing the ball checks to open. The oil is then transferred through the flow match valve from one side of the cylinder to the other, or one side of the rack to the other for rotary motion. Once the actuator has reached its desired set point, the motor stops and the ball checks are seated, stopping the flow of oil through the system. Now in the standby mode, power draw is only about 60 watts. The motors are brushless stepper or servo motor style, designed for 100% duty cycle and capable of very high frequency response, greater than 4 Hertz. The linear cylinders that we use are dual rod, so the oil volume exiting one side of the cylinder is equal to the volume entering the other side. The design eliminates both the requirement for an external reservoir and the need for continuously circulating oil through the system. This also leads us to another significant benefit of our technology: greatly reduced oil volumes. A small Rexa system, something that would require a smaller cylinder for lower thrust output and shorter stroke length, something like a desuperheater spray valve application, may only have a total of 8 to 10 ounces of oil in the entire hydraulic circuit, including cylinder. A larger Rexa circuit, one with higher thrust or output and longer stroke requirements, like one driving a governor control valve rack, may have as much as 2 to 3 gallons of oil total in the system. But this is a far cry from typical power plant control oil systems, which could have 500 to 1,000 gallons of oil in the entire system. Now that you're all experts on how the Rexa actuator works, let's move into some background on Longview Power. Constructed in 2011, it is a single unit 700 megawatt coal-fired plant with a best-in-class selective catalytic reduction system and flue gas desulfurization system. Longview Power is also considered a zero discharge facility. Okay, Buddy, can you tell us about a zero discharge plant?
Sure, Rich. Our zero discharge facility, all of our byproducts are sold or used for other purposes. We even have a deep well injection for the small amount of water that we do discharge. This goes into a mine pool at a much higher quality than the existing mine water, and then the outflow of that mine water is treated by another company, which we fully fund.
Wow, that's quite a process, and I'm sure new to a lot of us. Powering the Longview station is an advanced supercritical Foster-Wheeler boiler. And thanks to this design, high quality locally sourced coal, and additional efforts by Buddy's team, Longview Power has the lowest heat rate for a coal plant in North America at 8,750 BTUs per kilowatt hour. That's quite an accomplishment. This directly correlates to emissions, which are considerably lower than allowed by the plant's permit limits. It should also be noted that Longview is able to co-fire the boiler with natural gas when needed. All right, let's talk about some operational challenges the plant had. We were made aware that the plant was having problems with cooling water temperature control. As with many plants, the problem is compounded by cooling tower water evaporation and drift, which is water being carried out of the tower by the fans. In the case of Longview Power, a nearby river is used for makeup water. The challenge with this type of source is the varying water temperature depending upon the time of year. This next slide shows a cutaway of a typical cooling water circuit, also known as circulating water. The system starts in the basin at the bottom of the cooling tower. Water is pumped to the heat exchanger, or in this case, the condenser, absorbs heat, and then goes back to the cooling tower. You can see water is sprayed downwards against the air moving upwards, sucked in from the sides of the cooling fans. It is here that water can evaporate and drift up through the fans away from the cooling tower. Makeup water must be continually added to the basin due to this phenomenon. An important fact to remember is that circulating water temperature is actually controlled by the cooling fans. The need for additional cooling water is what brings us to the problems at Longview Power. A 16-inch butterfly valve powered by a motor operator was originally installed in this makeup line. It was unable to accurately control the flow of this varying temperature water to the basin. The result was large slugs of very cold or very warm water that was added to the cooling circuit, causing water chemistry to vary widely and the excessive use of chemicals. Okay, Buddy, this next slide shows a number of things going on in and around the cooling tower during these temperature shocks from poor water control. Can you tell us about them?
Sure, Rich. Starting with the basin water level. In a very rude control scheme, we were allowing our basin water to operate between -3 inches and +3 inches in just an open and closed control scheme. The makeup flow, shown in the blue line, was going from 0 to 8,000 gallons when we opened the valve, and then as the tower filled to 3 inches, we would close the valve and then allow the tower to evaporate off down to a -3, and then we would just simply open the valve again. We chased cooling tower chemistry during the early years to do this makeup control. As you can see by the trend, conductivity varied greatly. which is the tan line or the gray line in your trend. And this is very indicative of our other chemistry parameters.
Well, thank you, buddy. This next graph shows a trend in blue in the middle of the page, laid on top of the previous graph. Can you explain what this new trend line shows us?
Sure. The new trend line on here is our fuel flow into the pulverizers, our pulverizer coal flow. As you can see through the day, the coal flow continues to ratchet up all day long. This was a 37,000 pounds increase in coal flow throughout the day. This can be trended back in correlation to the water flow going to the cooling tower. And as every time we shut off makeup water to the cooling tower water would increase in this main circ water, and we would lose performance in our condenser, increasing back pressure. And the only way to make this up was to keep increasing coal flow into the boiler. As we increased the coal flow into the boiler, then we had to also increase boiler air, furnace draft, to compensate for the coal flow.
Wow, it's just amazing how all this cascaded back just from basin water level. So once you learned about REXA and our capabilities, you replaced the motor operator with a REXA. And based on what I've been told, it was simple to mount on your existing valve and even easier to calibrate. And I believe there was another requirement for this new actuator. It had to use your available 480 volt three-phase power. Is that right?
That's true. REXA provided stem to stern on this project. We were looking for a simple and economical replacement for the actuator and something that was easy to mount and change out. For us, given the remote location, an air operator was not an option either. At the remote location, we did not have ample access to our instrument air supply, so that was going to be cost prohibitive in building a typical control valve out there. But the REXA fit perfectly.
Well, that's terrific. From what I've seen, you immediately gained control of makeup water flow to the basin, and I learned that the excessive cycling of the cooling tower fans in colder weather was completely stopped. Is this true, and were there any other benefits?
There were several benefits, especially in the shoulder months where we are near approach temperature. We were cycling the fans on the cooling tower, stopping several times an hour. For a continuous operation plant like ours, we were leading into maintenance issues and preventative maintenance periods on these fans.
Wow, and I can see you have 20 of those cooling tower fans at 200 horsepower apiece.
That's 4,000 horsepower worth of fans that were starting and stopping several times an hour.
Wow. Well, all right then. This next set of graphs is from about 2 years after the REXA actuator was installed. These look considerably different from the previous graphs. Buddy, can you explain to us what's going on in this slide?
Sure. In this slide, we can see that the basin level, we're controlling plus or minus a half an inch. The circ water temperature, we're maintaining more consistent temperature, 64 to 67 degrees Fahrenheit. And then the makeup water is a key contributor to this. We're now, instead of cycling from 0 to 8,000 gallons per minute, we're maintaining a pretty consistent flow throughout the day between 2,700 and 4,800 gallons per minute. This also allowed us to maintain a lower condenser back pressure, resulting in more efficiency in the condenser.
Wow. Well, that's terrific, buddy. And then in this next slide, the pulverizer coal flow trend is different from the previous trend. Why is that so?
On this trend, you can see that the pulverized coal flow is much more stable throughout the day. This increase in control of the circ water temperature and the back pressure in the condenser led to a very much more stable coal flow. The increased stability in coal flow gave us tighter control over our emissions. Where previously we were cycling up and down with airflow in the boiler, we had to compensate by running excess air to control CO spikes, and we had to run excess ammonia to control the NOx spikes in the unit. Now we were able to bring excess air out of the unit, greatly improving our efficiency inside the boiler, and allowed us to run closer to our permit limits without having any exceedances.
Wow, that's terrific, buddy. We're all really glad to hear that. You know, it's hard to believe that gaining control of makeup water flow did so much to your plant. So let's review those things in this key takeaway slide. When a motor-operated valve actuator without any proportional control was installed on the main cooling water supply valve, these types of swings happen. The valve opens wide and shuts off. Then a true modulating Rexa actuator with a 100% duty cycle motor was installed, and the flow range became a continuous 2700 to 4800 GPM, as you mentioned before. Without thousands of gallons slugs of cold water added and then shut off to the circulation system, the cooling tower fans no longer needed to continually cycle on and off as they did before. And as you mentioned, maintenance on the fans was reduced considerably and in-house power use dropped. Responsible for makeup cooling water flow, basin level controls the makeup valve. With a steady level of plus or minus a half inch in lieu of the previous plus or minus 3 inches, large signal changes were no longer sent to the Rexa actuator. The valve is now allowed to modulate, which settles down the multiple operations of the cooling tower. Buddy, with your experience at the plant and having lived through improvements, would you like to comment on this bullet and the next few?
Sure. By improving the temperature delta in the cooling tower and the circ water basin, we've been able to optimize even the cooling tower performance where we were before running at a higher temperature to stabilize other plant processes that were coming off of the main circ water system. We were able to lower the entire circ water system and still maintain adequate control within the facility.
And then I guess this ties into this next bullet.
That's correct. As we were able to lower the circ water temperature without putting other equipment at risk, we were able to reduce back pressure. As you can see, 1 inch of mercury increase in turbine back pressure is a capacity hit of about 2%, but can improve efficiency by 160 BTUs per kilowatt hour.
All right, and then of course that ties back into this bullet here.
Correct. The pulverizer, once we stabilized the back pressure and we were able to stabilize the pulverizer cold flow, we were able to really tighten up on our emissions control and boiler combustion processes, also reducing fan loading and overall house power throughout the facility.
All right, and then we certainly can't forget what that does to emissions.
We were always running pretty well in hand on emissions, but we were overachieving in order to make sure that we didn't have any exceedances. And with the stable cold flow and tighter controls on our boiler O2 set points, we could approach closer to our permit limits without fear of having an exceedance. And we're also saving significantly on our ammonia usage for the NOx controls.
Well, that's correct, buddy. And I know you and I talking in the past, you had mentioned a payback time just for buying this one actuator.
Yes, sir. Typically, we look long-term in order to justify projects for the facility. And in this instance, going through and stabilizing water flow with the Rexa actuator, the project had less than a 2-month return on investment, which was very good for me, a good feather in my cap, and well received by management.
Well, that's terrific. That's a great note to end on here. So finally, remember, a Rexa actuator is not a product, but a solution that will make the difference for your plant on critical applications such as makeup water flow control. It's a sound engineering decision and an investment that will continue to carry forward.